This is podcast 3.1 for AP Chemistry, and we're going to get into gases and gas laws. Kinetic molecular theory are some assumptions that we make about gases to make our life easier. It says that these are properties of an ideal gas, and ideal gases are what we pretend all gases are because it's just easier that way. And in real life, if you were to base it off real gases, the difference that you would get in your calculations is not much. So kinetic means motion, molecular refers to molecules, so kinetic molecular theory of gases is really the moving molecular theory. We're going to abbreviate it KMT. The KMT postulates or assumptions is that the volume of individual particles of a gas are negligible. That means it's zero, doesn't count, it doesn't matter. The volume of a gas obviously has volume, but individual gas particles do not. The particles are always in motion, and they have collisions with the walls of the container. They exert no forces on each other, so they have no attraction for their neighbors that are around them in the container. And that the average kinetic energy is proportional to the temperature of the gas in Kelvin. So here we go with movement of molecules. All molecules move. And that should make sense unless they're at absolute zero and then they don't move. There should be a parenthesis there. Solids move vibrationally, so they just kind of vibrate in place. Liquids roll around each other, so they have enough movement that they can slide around one another. And then gases move in a constant random motion, just like we said. So they're always moving and they don't move in a predictable way. All right, so we want to know how fast do these gas molecules go. So what we do is we start with the kinetic energy equals 1/2 mv squared, and that should sound familiar to you. If we take that and we rearrange it, so we have kinetic energy equals 1/2 mv squared. If we solve for v, so I'm going to not do it for you, but if we did it, we would come out with this formula right here. So velocity is going to be equal to the square root of 2 times the kinetic energy over m. And for this one, mass is going to be in kilograms, and velocity is going to be in meters per second. So doing this, we get that. But then we use the other formula for kinetic energy, which is 3/2 RT. And R in this problem is 8.3145. And it is, I'm trying to think of the units, joules per mole Kelvin. So if we take this right here, plug that in for kinetic energy, what we end up with is this. 3 times R times T, and that T would be in Kelvin, over big M. And big M is kind of like molar mass, except instead of being in grams per mole, it's in kilograms per mole. So you just got to watch out for that. But we like that formula because it lets us calculate how fast these gas molecules are moving. And you're going to see it abbreviated like this. So instead of V, you're going to see this U and then subscript RMS, and that means the root means square velocity. How fast are these things going? And then again, that's the value that you'd plug in for R, the temperature is T, and then M is the mass of 1 mole of gas particles in kilograms. So it's going to be kilograms per mole is what you're going to use for big M on the bottom. Okay, so here's an example problem doing that equation that we just found. It says, find the velocity of an oxygen molecule in this room. And in this room, we're assuming most rooms, which would be a temperature of 21 degrees Celsius. And we said that that's equal to the square root of 3RT over M. So there's a couple things. T we said is always in Kelvin. So instead of 21 degrees Celsius, we would add 273 to that. And we're going to use 294. We know what R is, it's that constant. We need to find the mass though, and we need it in kilograms per mole. So if oxygen is normally 32 grams per mole, we can just bump over the decimal and make it 0.032 kilograms per mole. So there are all of our values. We know R, because it's 8.3145. So I'm going to take those and I'm going to plug them in to our equation. The square root of 3 times 8.3145 times temperature, which was 294, and we're going to divide that by our 0.032. And if we do all of that, we end up with 478 meters per second, which if we did the conversion would come out as 1,069 miles per hour. So those oxygen molecules are booking it. They're moving fast. The reason you don't feel them, which you probably realized, is, I mean, that thing is moving and you would think if that hit me I should be able to feel it. The mass of these things are so tiny that you're just not going to feel them even if they're moving that quickly. So oxygen molecules, they're moving pretty fast. Alright, the next thing we need to talk about with gases is the difference between diffusion and effusion. So this guy right here is a prime example of diffusion. We have gases from his body mixing with gases from the room. And then with effusion, we have a gas that's in a chamber and it's escaping into an empty area. So I always think effusion, empty chamber, they go together. Diffusion is when you have different gases mixing. So here's our definitions right here. Diffusion describes the mixing of gases, and then effusion describes a gas moving into an empty chamber. So with this, we have a couple different formulas that we can look at. The distance traveled by a gas divided by the distance traveled by gas number 2 is equal to the square root of the molar mass in kilograms per mole. Well, I think in this one it's okay if you use grams per mole because the units will cancel. So if you use kilograms per mole and kilograms per mole, it would be fine because they cancel. So in this one, it's okay if big M is in grams per mole. You don't need to do the converting because we just need the ratio. So the distance by gas 1 divided by the gas 2's distance is equal to the mass of gas 2 on top divided by the square root of the mass, molar mass of gas 1 on the bottom. So 1 and 1, 2 and 2, like that. And then if we're talking about effusion, we talk about the rate of effusion, and it's the same. Your gas 1 and then your molar mass would go on the bottom, gas 2 and then your molar mass for that would go on top. This is also referred to as Graham's law of effusion. And what we know about these, if I wanted to draw a picture, you could do what we did back there. But conceptually, what we need to know is that how fast something effuses or diffuses is related to its mass. So, just like people, the more massive the molecule, the slower it's going to go. The more massive molecules move slower. So the smaller they are, the quicker they go. The bigger they are, the slower they go. And then we have our equation for Graham's law right there. We can use this in an example problem here. It says, calculate the speed of hydrogen molecules at 295 Kelvin and then use Graham's law to find the speed of uranium hexafluoride at the same temperature. So the first thing I want to do is calculate the speed of a hydrogen molecule. So I'm going to use that first equation that we talked about, square root of 3r And then the temperature, let's just pick one because it doesn't matter. So we'll say, oh, temperature's right there. I don't need to pick one. So we'll say 295 Kelvin. And then hydrogen we want in kilograms per mole, so it'd be 0.002. And if I take that and plug it into the calculator, I get 1918 meters per second. Okay, so that is the answer to your first problem. Calculate the speed of the hydrogen molecules. Then I want to use Graham's law. And Graham's law said that the rate of my first molecule and then the rate of my second is equal to the square root of the molar mass of my second over the square root of the molar mass of my first. It doesn't matter what goes where, so you can put your unknown wherever. What I'm going to do then is I'm going to say that rate 1 will just make it hydrogen. So gas 1 is going to be hydrogen. Gas 2 is going to be my uranium hexafluoride. So that will be 1918. That's the speed or the rate that it's going to move at. And then rate 2 I don't know because that's what I'm looking for with the uranium hexafluoride. I can use the grams per mole in this. So if I add up uranium hexafluoride, I'm going to get 352 grams per mole. And that needs to go opposite. And then that means that my hydrogen would go down there. And if I take all that, plug it in, solve it, rearrange it, do what you need to do, you're going to end up with 144 meters per second. So your hydrogen is moving at 1918 meters per second. Your uranium hexafluoride is only moving at 144 meters per second. So there is a significant difference, but there is a significant difference in the size of these molecules. All right, and this is just a visual that you can see and look at here. You can see how this is such a big molecule, and this is speed. A lot of the molecules are moving much slower as compared to hydrogen, where they're around here, 1500 or so. You can see it kind of peaking. But with the uranium hexafluoride, it's way down here at the bottom. So you can see just what we found out in a visual form. And then the second part of this says, how much faster is hydrogen than chlorine? So our additional problem is asking us to find kind of a whole number ratio. We want to know, is it 2 times faster, 3 times faster, what's faster? So the hint to solving these types of problems is setting the larger molecule's rate equal to 1. So if I'm doing that, I want to solve for the hydrogen then, because my larger molecule is chlorine, and we're going to say that chlorine's rate is equal to 1. So what I'm looking for is hydrogen. What's hydrogen's rate? So if I do that, I'm just going to put x on top to make my life easier when I'm solving for math. And then I have 1, because that's what we said chlorine was. So remembering on the other side, I need to go opposites. And that would not be opposite, so let's try that again. I'm going to put x over 1, and then I'm going to put chlorine's mass on top, which is roughly 71. And then I need to go opposite the unknown, which is going to be 2 for hydrogen. And if I do that and I solve for x, we end up with 5.95. So what that tells me is that hydrogen is about 6 times faster than chlorine. So when you're trying to figure out how much faster, they're not saying what is the rate. That's when you want to set the larger molecule's rate equal to 1, solve for your other because it's going to be a 6-to-1 ratio. So hydrogen's going to be traveling approximately 6 times faster than chlorine, and you'll see those problems occasionally. All right, last thing here with temperature, just kind of some information you need to know. Temperature is the average kinetic energy of a molecule in a sample, and we should understand then that the higher the temperatures means that those molecules are moving faster. And when we're using temperature with gas laws, make sure that we're always using temperature, or make sure that we're always using Kelvin. Ooh. When we're talking gas laws here. All right, pressure and its units. So pressure is caused by collisions with the walls of the container. It's equal to the force per unit area, P equals F over A. And then it's measured with a barometer. And we have all sorts of barometers. Here's an example of one. It's called a manometer. You have your gas sample right here. There's a mercury column in between here. And then this end is just open to the atmosphere. So what we can do is we can tell that if the atmospheric pressure is pushing down, it's causing this column, the difference, to look like this. We know that the gas within this little flask right here is less than atmospheric pressure, because pressure from the atmosphere is being able to push kind of into this flask. It's able to push the mercury farther down. On the other end, though, if we have it set up like this, where the gas that we have in here is causing the mercury to get pushed farther up the tube towards the atmosphere, then we know in this situation the pressure in the flask is greater than atmospheric pressure. So these are two simple ways that you can figure out the pressure of a gas sample that you have. Of course, we don't do that anymore. We have digital barometers that do that for us, because they don't let you have mercury in class anymore. This is a Torricelli barometer. It's named after the guy who made it up. It's filled with mercury. There's a vacuum up here, so no air. It's all escaped. And then you can tell that just by the height of the barometer. The height of this column of mercury will tell you the pressure of whatever it's sitting in, the air out here. So some pressure units that you need to know: 1 atmosphere is equal to 760 millimeters of mercury, which is the same as torr, because we named millimeters of mercury and torr. They're the same thing after Torricelli. That's also the same as 101.32 kilopascals and 14.7 psi. So our question here is: a meteorological map shows the barometric pressure at 99.8 kilopascals. What is the pressure in all those different units? So we would just do a quick little dimensional analysis problem here. I'd start with what I'm given. If I'm trying to go to millimeters of mercury, then I would look up here, and I would see that for every 101.32 kilopascals, I have 760 millimeters of mercury. And if I plug that into my calculator, I get 749, and I would do millimeters of mercury. So since millimeters of mercury and torr are the same thing, that means my A and my B answer are going to also be the same. So that would also be 749 torr. And then to go to atmospheres, I could just use that again. But I just, oops, not kilograms. Ooh, kilopascals. And I would put my 101.32 on the bottom, and then I would just put 1 atmosphere on top. So if I plug that one into the calculator, I get a little under 1 atmosphere, which makes sense because if this is 99.8 and that's equal to 1 atmosphere, I should get a little under 985. So that would be my atmospheres. And then to get to PSI, maybe I start with this answer this time. So 985 ATMs. Well, 1 ATM is 14.7 PSI. So if I do that in my calculator, I end up with 14.5. So those are your answers if you wanted to just practice converting between all your pressure units. That should be review from last year. All right, we're going to talk about all the different gas laws. So Boyles Law, Charles Law, Lusak's Law, and then Avogadro's Law. All right, The first one is the relationship between pressure and volume, which is Boyles' Law. And he found out that as pressure increases, the volume decreases, and that is illustrated in this picture here. We have a piston type setup. As we increase the pressure on the top of this canister or on this piston, the volume is going to go down. So what he found then with that is that what this says is as pressure increases, volume decreases. So that means that they are inversely, that's an I, proportional. As one goes up, the other goes down. And we can do a graph and an equation. So the equation for this, which hopefully looks familiar, is P1 times V1 equals P2 times V2. That's the formula you use with Boyles' Law. And this is if temp is constant. So don't forget, temperature has to be held constant. And then for the kind of graphs to illustrate this, if you graphed pressure versus volume, you're going to get kind of a curved graph like this. You can see as pressure goes down, volume goes up. But what they like to do to get a nice linear relationship is they do pressure versus the inverse, I guess, of volume, or 1 over volume. And what you end up with is this nice straight line that looks like that. So those are the two graphs that are represented with Boyles' Law. Okay, the other thing, or the next one, I guess, would be volume versus temperature, and that's Charles' Law. So Charles' Law, what he figured out is that as temperature increases, volume also increases, which means as temperature decreases, volume also decreases, and that's illustrated in this picture right here. We have our Eskimo -10 degrees Celsius, and the balloon's pretty small. We work our way up to a guy on the beach grilling, and you can see that the volume of the balloon has changed drastically. So as temperature goes up, so does volume. As temperature goes down, so does volume. That means that they are directly proportional. And the other way you can think of it is if you take a balloon, that is a balloon, and you put it over a fire, well, you know what's going to happen. That balloon's going to get bigger. So you have some experiences from the real world that tells you that this is what will happen. So going to the graph and the equation then, this is going to be at a constant pressure. The graph with this, oh, actually let's do the equation first. V1 over T1 equals V2 over T2. So if I know the volume and temperature in one situation, and I know the temperature in the second, I can calculate the volume. What your graph is going to look like is V over T, and if we graphed it, it would be a nice straight line like this, because they're directly related. Remember that when we're talking with these, this has to be in Kelvin. In Kelvin. So make sure your temperature is in the correct units. All right, the last one here is pressure and temperature. And here's an example. We have a flask with some gas sitting in an ice bath, and then we have the same flask sitting in boiling water. And you know that the higher the temperature, the faster the molecules move. So the faster the molecules move means more collisions with the walls of the container, which means pressure is going to go up. So slower molecules, less collisions, less pressure, and that's read here at a pressure of 1 atmosphere. Then in our boiling water here, with the molecules moving a lot faster, we can see an increase in our pressure right there. So as temperature goes up, pressure goes up. And as it goes down, so does pressure. Directly related, just like that. And then the equation for this is going to look a lot like the one we just wrote. P1 over T1 equals P2 over T2. And our formula, or not our formula, our equation, P over T is going to be the same way. So straight line looks like that, remembering that this is in Kelvin. And you can use any units of pressure that you would like. We like to take these and put them all together, and that is called the combined gas law. And that is P1 over V1, or P1 times V1 over T1 equals P2 V2 over T2. And this should hopefully look very familiar to you. We used it a lot. And remember, when things are held constant, when a variable is held constant, you can just disregard it. We'll just say cross it out. So you don't have to remember all the individual laws. You can just use this one. And if we're talking at a constant temperature, you just get rid of temperature down there and you just use that and you'd be left with Boyles Law. So you don't have to remember the individual ones. You can just remember the combined gas law. Okay, so it says we have Wilson, and we're pretending Wilson is that guy in the picture there on your paper. That's a balloon. Wilson is at the top of Pikes Peak, and he's also on the beach, and we want to know what would be his volume on the beach. They gave you some information that we need to know, like the volume of him on Pikes Peak is 1 liter. So we'll say V1 is 1 liter. We also are given that the temperature on Pikes Peak is 273 Kelvin. And then the pressure on the top of that mountain is 0.55 atmospheres. So on the beach, we do not know, that would be V2. We don't know what his volume is. We know that the temperature on the beach is 303 Kelvin and that the pressure at sea level is 1 atmosphere. So if we have this here, we can solve for a known volume by using our combined gas law that we just talked about. So with that, we just kind of plug and chug. So this would be 0.55 times 1 liter over 273 Kelvin equals my 1 atmosphere times the volume that I don't know over 303 Kelvin. So doing all of that, we would find that V2 is equal to 0.610 liters. So if we look at that for a second, on the top of Pikes Peak, Wilson would have a volume of 1 liter. When we get down to the beach where the atmospheric pressure is roughly doubled, it's quite a bit more, you can see that the volume of Wilson would decrease, so the balloon size would actually go down. That is a little weird because you're going from a colder temperature to a higher temperature, but the change in pressure kind of is greater than the change in the temperature, so it overrides it and Wilson would still get smaller. All right, Avogadro's law talks about moles of a gas and how they're related. If you wanted to throw that into the combined gas law, it would go on the bottom. Moles are equal to N in this. So it would go on to the bottom with the temperature. So P2 over V2, or P2 times V2 would equal T2 times N2. So Avogadro did a lot of studies with moles of gases and things at certain temperatures. And if you wanted to, you could plug in moles and use it in the combined gas law as well. Okay, we'll get to that later on. The ideal gas law is actually a form of the combined gas law. We want to derive it. So just what I wrote there, the P1 V1 over T1 and N1 equals P2 V2 T2 N2. What I would do is I would take this and I would say, let's make this equal to STP conditions. And so that's going to be 1 atmosphere of pressure. The volume is 22.4 liters, and we'll talk about why that is later. Temperature is 273 Kelvin, and the moles is 1 mole. Avogadro found that 1 mole of any gas at STP has a volume of 22.4 liters. It doesn't matter what the gas is. So that's what we plugged in here. And if you do all of this, you end up with PV over Tn is equal to 0.08206. And that should look awfully familiar, like you've used it before, because that is one of the gas constants. The liter atmosphere over mole Kelvin, that's what we call R. That's another version of R. So doing all of that then, if PV over Tn equals R, then we just rearrange and get PV equals nRT. And that's where the ideal gas law comes from. The ideal gas law is used for constant conditions, not changing conditions. You're looking for an unknown variable in one set of conditions. The combined gas law is used for changing your conditions. So they're used in two different kind of areas. And then here's that ideal gas law again. So pressure needs to be in atmospheres, volume, liters, N is moles, R is that gas constant that we just derived, and T is your temperature in Kelvin. We can have another example then with Wilson, our balloon. Wilson is filled with oxygen gas. He has a volume of 3.25 liters and is at 22 degrees Celsius and 0.75 atmospheres of pressure. How many grams of oxygen are in Wilson's head? So we're going to use PV equals nRT, and the clue that they gave me is if they're talking about grams or moles, we need to use the ideal gas law. The pressure that they gave me is 0.75 atmospheres. The volume is 3.25 liters, equal to, I do not know N. N is moles, and when I find moles, I can quickly go to grams using the molar mass in the periodic table. R is that gas constant, and T is going to be 22 plus 273, so it's going to be 295. And if I do that and I solve for N, I'm going to end up with 0.1007 moles of oxygen. And that's not the end. Remember to go one more step. That 1 mole of oxygen is 32 grams. And when we do that, we end up with 3.63 grams of oxygen. So how many grams of oxygen are in Wilson's head? 3.63 grams of oxygen. And that is it. So we're going to stop there with gas laws. We'll do more practice in class with them. But after this, we're going to get into partial pressures and using gas stoichiometry and the ideal gas law together. So make sure you come to class with questions, and we will definitely do more practice.